Today we are going to talk about another type of relationships which are called quadratic. In this type of relationships, when you plot the graph of the two variables, what you get is not a line anymore. You're going to get a curve. Now, we will define a quadratic relationship, a relationship which has the following characteristics. The first characteristic is that the second differences are equal. To refresh your memory, if I have a table of values, let's say x and y, the y values are given. If I find the difference between the two consecutive y values and I write them here, this is called the first differences. Now, in a linear relationship, these first differences are all equal. But there are cases like quadratic relationship that the first differences are not the same. If you find the second differences, meaning the differences between these two first differences, you get what we call the second differences. In a quadratic relationship, the second differences are all the same. They are equal. The second characteristic of a quadratic relation is that the graph is a curve, which we call a parabola. Meaning, if I plot the graph of a quadratic relation, I will get something like this one or something like this, which is obviously, it is not a line, so it's not a linear relationship. And the third characteristic is that I can write the relationship between the two variables in a standard form, y equal ax squared plus bx plus c, where a, b, c are real numbers, with the main condition that a cannot be 0. Because just remember, if a is 0, this x squared is going to be gone, and what you are going to be left with is a linear relationship. So these are the three characteristics. Again, in table of values, the second differences are equal. If you plot the graph of x and y, you get what we call a parabola. And the equation can be written as ax squared plus bx plus c. Now we are going to go ahead and start doing a couple of examples. The first example is asking us to show which one of these table of values represents a quadratic relationship. What I did is I wrote these two table of values vertically. So 0 and 250, I wrote it in the first row, and then 1, 238 here, and so forth for both of them. Then to find the first and second differences, you take every y value, 238, and subtract the one previous to it, 250. So 238 minus 250 is minus 12. 202 minus 238 is minus 36. 142 minus 202 is minus 60. You can see that the first differences here, they are not the same. So what we can say is that this is not a linear model, because the first differences are not the same. I continue to the second differences. I do the same thing. Minus 36 minus minus 12 is going to give me minus 24. Minus 60 minus minus 36 gives you minus 24. You can see that the first differences are equal. Then I can say that this is a quadratic model, and I do not continue anymore to go to third differences and so forth. The second example, I wrote it again in vertical form, 0 and 32. I wrote it as 0 and 32, and so forth, 148, 148, and I continued with the table. Now, the first difference is 48 minus 32 is going to give me 16. 72 minus 48 gives me 24. And 108 minus 72 gives me 36. Since the first differences, as you can see, they are not the same, this is not a linear model. So I'm going to jump to the second differences. The second differences is 24 minus 16 is 8. 36 minus 24 is 12. Again, you can see the second differences are not the same. So that tells you that this relationship is not even quadratic. So it's not linear and it's not quadratic. In the next example, I have a curve which looks like a parabola, and it's asking me, is this a quadratic relationship? And since the curve is a parabola, I can say that this one represents a quadratic relationship. The next example is giving us a graph which looks like a line. So I can say that this is a linear relationship and it's not quadratic, again, because the graph is not a parabola. So this is not a linear relationship. I'm sorry, this is not a quadratic relationship. The next example is y equal x squared plus 7. Remember that we said that if it is a quadratic relationship, the equation can be written as y is equal to x squared, ax squared plus bx plus c. If I compare it with this one, which is x squared plus 7, you can see that the term bx is not here. So I'm going to rewrite this one as x squared plus 0x plus 7, because 0x is 0. Now you can see that a is 1. Compare the coefficient here, which is 1, with a. Compare the coefficient here with b. So b is 0. And c is equal to 7. Then I can say that this is really a quadratic relation. The fastest way to detect if it's quadratic or not, look at the maximum exponent of the variable x. The maximum exponent is 2 here. Any equation with the maximum exponent, or what we call the degree of the equation, to be 2 is called a quadratic relationship. So this is a quadratic. The next example is y equal 3x plus 2. Again, going back to previous example, you can see that the exponent of x maximum is 1 here, because the exponent here is 1. So the degree of this equation is 1 and it's not 2. So this is a linear relationship. It is not quadratic. The next example is the formula d is equal to 0.5 at squared, where d, a, and t are all variables, which gives you the distance traveled by a car as it accelerates from a stopped position. D, which is in meters, is the distance traveled. A is meters per square second is the acceleration, and t seconds is the time elapsed. We are supposed to find the relationship between D and A, if t is equal to 2. If t is equal to 2, I get D is 0.5 A times t squared, so 2 squared. So from here, D is 2 squared is 4. 4 times 0.5 is 2, is equal to 2a. I have to investigate what is the relationship between D and A now. You can see that the maximum exponent of A is 1, so this means that the relationship between D and A is linear. And if you remember from grade 9, Since the y-intercept is 0, this means that the relationship is direct, meaning that it goes through the origin. So if I plot this one as d, this one as acceleration, I'm going to get a line which goes through the origin. So this is the investigation to find the relationship between D and A. The next part of the example asks us to find the relationship between D and T when A is equal to 2 meters per square second. Remember that the equation was D is 0.5 AT squared. Now if A is 2, we get D is 0.5 times 2t squared, which is t squared. Now if you look at this equation in terms of D and T, the exponent of t is 2, the degree of this equation is 2. As we said before, any equation with degree 2 is a quadratic relation, and the graph between D and T is going to be a parabola. Now if I plot this one, I'm going to get something like this curve, which is a parabola. The next part of the question says, what type of relationship were obtained in parts A and B? Why does it make sense that these relationships were obtained? In part 1, we said when t is constant at 2, then we found a linear relationship between D and A because the exponent of A was 1. And the second part, when A is 2, we found D is equal to t squared. The exponent of t was 2. We said because the degree is now 2, this is a quadratic relationship between D and T. Now the last part of the lesson talks about quadratic regression. As we said about linear regression, this is the process of finding the parabola of best fit for a given set of data. What it means is that if I plot the data points, something like this one, or if I have the related table of values x and y with given x and y, remember that this table of values when plotted gives you this scatter plot. What you're supposed to do in quadratic regression is to find the quadratic of best fit which goes through these points. This is called the quadratic regression, like the linear regression that we did in the previous lessons. Now, the good thing about quadratic regression is that if you can find the curve of best fit or quadratic of best fit, then using this quadratic of best fit, because I know the equation now, in general is ax squared plus bx plus c, I can use this equation to interpolate or extrapolate values. This means I can predict or forecast values of y if x is given, or vice versa, or values of x when y is given.